Welcome to ChemSphere Hub. Today we will discuss on factors affecting the UV visible spectrum of a compound. UV visible spectroscopy is one of the most powerful techniques in analytical chemistry for studying electronic transitions in molecules, detecting chromophores, and understanding structural features. Today, we will explore how different molecular and environmental factors influence UV absorption, shift, lambda max, and modify intensities. These concepts are essential for researchers working in chemistry, pharmaceuticals, environmental science, and materials engineering. To begin, let's quickly revise what is UV visible spectroscopy means. UV light ranges from 200 to 400 nanometer, while visible light ranges from 400 to 800 nanometer. When a molecule absorbs UV radiation, its electrons undergo transitions from a lower energy state to a higher energy state. As we can see that UV range is 200 to 400 nanometer and visible range is 400 to 800 nanometer. Electronic transitions depend on the energy gap. The absorption wavelength depends on energy gap delta E between molecular orbitals. This energy is related through the formula delta E is equal to H mu, that is equal to Hc over lambda. So as delta E energy decreases, the wavelength increases. The UV spectrum reflects these transitions and provides structural information. In UV spectroscopy, the main transitions we study are sigma to sigma transitions. These are highest energy transitions and require deep UV radiations. Pi to pi star transitions. They are very common in conjugated molecules and they absorb strongly. N to pi star transitions. They involve lone pair of electrons like carbonyls or heteroatoms. The UV spectrum is primarily influenced by pi to pi star transitions and N to pi star transitions. Allowed transitions have high molar absorptivity. However, forbidden ones appear as weaker. Understanding these transitions helps us interpret changes in lambda max as we change structure, solvent, and pH. Factors affecting UV spectrum. Here we will analyze 10 major factors, which are conjugation, substituent effect, solvent effect, pH effect, chromophore nature, oxochromes, geometry and steric effects, concentration effects, temperature effects, and instrumental parameters. Each of these factors influence either the position or the intensity of UV absorption. Conjugation is the most important factor. When a molecule has a series of overlapping p orbitals, electrons become delocalized. This delocalization reduces the energy gap between the HOMO and LUMO. According to the relation lambda is equal to Hc over delta E, a decrease in delta E increases lambda max. Thus, greater conjugation Thus, greater conjugation, lambda max shifts to longer wavelength and results in bathochromic effect or redshift. On the other hand, when conjugation breaks, the absorption shifts to lower wavelength like hypsochromic effect. Let's look at a simple comparative example. Like ethene absorbs around 171 nanometer. When we extend conjugation to 1,3-butadiene, lambda max moves toward 217 nanometer. As we discuss here, the ethene lambda max is at 171 nanometer. However, 1,3-butadiene lambda max is at 217 nanometer. And if the delocalization of electrons increased, then benzene lambda max shifts towards 254 as of longer wavelength. Now we will discuss the substituent effect. Substituents also dramatically influence UV absorption. Electron donating group like hydroxyl amino increases electron density in the chromophore. This stabilizes the excited state more than the ground state, reducing delta E, resulting in a redshift. Electron withdrawing groups like NO2, C double bond OH, chloride withdraw electrons density, destabilize the excited state and increase delta E, causing a blue shift. So substituents change the electronic environment and directly affect lambda max and absorbance E max. How the oxochromes affects. An oxochrome is a functional group that does not itself absorb UV strongly but modifies the absorption of a chromophore. Example includes OH group, NH2 group, OR groups. Oxochromes increase lambda max and also increase absorbance intensity because they enable partial conjugation or electron donation. This is why phenol absorbs at longer wavelength as compared to benzene. These are the examples of oxochromes. Solvent's polarity plays an essential role for N to pi star transitions like in carbonyls. Polar solvent stabilizes the ground state more than the excited state. This increases delta E leading to a flow shift, so lower lambda max. And for pi to pi star transitions like aromatic rings, the excited state is stabilized more than the ground state. And delta E decreases and it results in the redshift with higher lambda max. Therefore, solvent's choice can drastically change spectral readings, which is why UV measurements often specify ethanol, methanol or water as the solvent. Now we will discuss the pH effects. pH changes that alter the ionization state of a molecule. In acidic conditions, groups may become protonated, disrupting conjugation, causing a blue shift. In basic conditions, Groups may become deprotonated, increasing conjugation, causing a redshift. For example, phenol in basic medium becomes phenoxyidine, which has extended conjugation and absorbs at lower wavelength. In acidic medium like aniline gets protonated to form aniliniamine, losing conjugation and shifting to lower lambda max. However, in basic medium, phenol becomes phenoxyidine, increasing conjugation and shifting lambda max upwards. Thus, pH strongly influences the compounds containing OH and NH2 groups and other ionizable groups. Now we will discuss the nature of chromophore. The chromophore is the part of the molecule responsible for light absorption. Different chromophores absorb at different ranges, like carbonyls have characteristics N2 pi star absorption. Aromatics, they have strong pi to pi star transitions. Nitro compounds, they strongly absorb in UV region. Transition metal, like transition metal complexes show D to D transitions often in visible range. Understanding the chromophore helps predict UV absorption behavior. Molecular geometry greatly affects pi overlap. For example, in conjugated dienes, the trans form typically absorbs at longer wavelength compared to the cis form because it allows better overlap. Steric hindrance twists the molecule out of planarity, reducing conjugation, leading to a blue shift. Thus, 3D molecular shape is essential in UV analysis. The relationship between absorbance and concentration is expressed by the Beer's-Lambert law. A is equal to ECL, where A is absorbance, E is epsilon is molar absorptivity, C is concentration, and L is path length. Absorbance increases linearly with concentration only within a varied range. Very high concentrations lead to deviation because molecules interact, scatter light, or aggregate. Temperature affects molecular motion. Higher temperature causes a peak broadening, small shifts in lambda max, and sometimes reduces intensity. Instrumental factors include slit width, light source, detector sensitivity, and also baseline noise. Now we can discuss the as we look at benzene derivatives, aniline and nitrobenzene. Aniline absorbs at longer wavelength than benzene due to electron donation by the NH2 group. Meanwhile, nitrobenzene absorbs at a shorter wavelength because NO2 withdraws electrons. This demonstrates how substituents influence absorption behavior. To summarize the main factors affecting UV spectra, we discussed conjugation, electron donating groups, electron withdrawing groups, polar solvents that shift N to pi star, transitions to shorter wavelength, pH changes, ionization and conjugation, geometry and steering factors that alter pi overlap, concentration and instrumental factors affecting intensity and accuracy. A complete understanding of these factors improves spectral interpretation. And in conclusion, UV spectroscopy provides essential information about molecular structure, electron distribution and environment. Knowing how these factors influence UV absorption allow chemists to control conditions. Thank you for your attention. Like, share and subscribe my channel Chemsphere Hub.